in the registers, this another interesting feature that this ARM processor has. So, there are 16 general purpose registers marked R0 to R15 in user mode. Okay. So, user mode is basically the mode in which the processor is generally in when it is executing some program. So, it is it has got R0 to R15. So, as an user, so I can use this R0 to R15 registers. Out of these 16 registers, R15 is the program counter. Okay. So, unlike other processors that we are familiar with, where the program counter was a special register and there are only a few instructions by which you can access the program counter. For example, in case of 8085, you remember there was an instruction PCHL by which this program counter was accessible, or you can make some call to subroutine by which the program counter value will be available in the stack and do the manipulation there. So, that way we can do it, but you can just in case of ARM processor it is not that. So, R15 is available to the user for as a general purpose register as well. Then the R13 register is conventionally used as stack pointer. So, please note the term conventionally. So, means that there is no hard and fast rule that I have to use this thing R13 as the stack pointer. So, I can use that R13 as simple register also, as a general purpose register also, but in general, so it is used as stack pointer. And this is another thing to note, that the ARM instruction set, it does not have push pop instructions. So, there is no push pop type push pop instructions in ARM. So, you do not have these stacks available in ARM. So, it seems very surprising, because the program that I am writing, so there may be sub programs and all that. So, if the stack is not there, so how am I going to save the return addresses of the subroutines, and how am I going to pass parameters like that. So, there are many concerns. So, what this ARM people thought possibly is that it depends on the program. So, many programs may not need to call a subroutine. So, it may be that it is just written in a flat fashion. So, the entire code is a single routine. Okay. So, there is no sub program. So, as a result, I do not need any stack in that case. So, why should I have that burden of stack? So, if I need stack, so I can use it, I can define it in some in my own way, that we will see later, but by default this ARM does not have any stack pointer. Okay. Now, this R so if you are using a stack, if you are defining a stack, in that case this R13 is used as the stack pointer, but that is a convention only. So, if this is not there, if the stack is not there, then the biggest disadvantage that we have is the calling and returning from sub program. So, what this ARM has done is that they have dedicated this register R14 called the link register. So, whenever a procedure call is made, the return address is automatically placed into this register, and the return from procedure is simply by copying R14 to R15. So, let us take an example. Say I have got a program, and somewhere I am calling a subroutine, call say subroutine ABC, and the subroutine ABC is somewhere here. Okay. So, here it is doing at the end I have got the return from subroutine. Now, what this if this is say the address is say 1000 and this instruction is say 3 byte instruction, the next so next location is 1003. What the ARM people will do, the ARM processor will do is that in the link register, okay, so in the link register, that is in R14, it will put this value of 1003. In R14, it will put the value 1003, while this call is being executed, it will be done like this. Now, when it comes to this point, so return exclusive return is not necessary. So, what you can do, R15 is the program counter. So, you can simply say move R15 comma R14. So, what will happen, this R14 will be copied into R15, and as a result the program counter is now modified. So, you are back to this point. So, the program will continue executing. So, it is like the return from the subroutine. So, this way it is fine. So, so what is the what may be a possible advantage? The possible advantage that we have is, you see, there is no memory access. So, if you consider say 8085, so if this is the 8085 processor and you have got this as the memory, a part of the memory is defined as a stack, okay, and the top of the stack is pointed to by the stack pointer. So, whenever a subroutine call is made, so the PC values are saved onto this register. So, PC low and PC high, so they will be saved onto this stack, and for returning, so these values will be popped out from the stack. That means, whenever it is going for a procedural call or subroutine call, it is doing a memory access, and returning also it is doing memory access. So, that is time consuming, that is power consuming. So, external bus activities will be there, address bus, data bus lines, there will be activities. So, we will have those time and power consumptions will come into picture. But here what is happening is that see R14, R15, they are all internal registers. Okay. So, they are within the CPU. So, there is no difficulty. So, they are simply register to register data transfer. So, that is very fast. So, that way it is a very convenient way of doing this subroutine call, okay, when you are calling a single subroutine. But of course, there is a catch, like if you so whenever you are within the routine ABC, if there is another call to another routine XYZ, then what will happen? So, if this is starting at say location, say suppose this is the next instruction is at location say 2004, okay, then while this call is being executed, this R14 will get overwritten with the value 2004. Now, coming back, so coming back whenever this XYZ routine is over, so suppose this is the routine XYZ, and then when you are, whenever you are trying to go back, so here you have to put that instruction move R15, R14. So, where will it come back? So, it will come back to this location, but by that time your R14 register content is lost. So, this value that we put here, this 1003, that was put there. So, by this time this return value is lost. So, you will not be able to return this one properly. So, this return will not work. So, basically you need to do something extra to take care of this type of situation. So, whenever you have got this nested procedural call, we have got difficulty. Okay. But in a program I may not have nested procedural call. So, as a result this may not be necessary. If it is necessary, then I have to take special care, like I need to save the content of this R14 register onto stack, and while returning from here. So, I have to just pop out the content from after returning here, I have to before calling this I have to push this R14 register value into stack, and after coming to this point I have to pop out the R14 register from stack. So, somehow the stack will be necessary, but that is program specific, and the programmer if needed will be implementing the stack himself. Okay. So, the basic processor will not support it. Now, so that is the R14 is the link register, and it has got when a procedural call is made, the return address is saved in this R14 register, and return will be done by copying R14 to R15. Then there is a program status register, there is a current program status register, and there is a number of stored saved program status registers. The number of such SPSR registers are there. So, current program status register, it has got 4 condition flags, negative, 0, carry and overflow. So, there is nothing like auxiliary carry and things like that. So, it has got only 4 bits, negative, 0, carry and overflow, and there is a SPSR register that can save the content of CPSR register in some modes of operation. So, if you look into the modes of operation, then the ARM processor can execute in different modes. Okay. First one is the user mode, when the program is executing some application code. So, in general I can say that whenever you are looking into a processor operation, so the operations can be classified into different category. The basic mode is the user mode of operation. Now, in user mode of operation, so we have got this program statements like x equal to y plus z, if a is greater than b, then x equal to c minus d. So, like that we are writing program. So, as long as it involves only memory access and some arithmetic logic operations, so they are program will be executing in the user mode. But sometimes what is needed is that maybe we want to output the value of x, maybe we want to put it onto the screen or put it onto the printer, the value of x has to be put onto the on some device. So, in that case how is it implemented, because if this access is unrestricted, like in a system I can have a number of user programs executing, and if I do not have any control over this thing, like which program will access the device and all that. So, there will be a full chaos. Okay. So, what is normally done is whenever a device whenever a program requests this type of service, so they are known as services from the operating system or OS services, and whenever these operating system services are necessary, we go from user mode to something called user mode to system mode or kernel mode. So, this is called user mode to system mode or kernel mode, and this execution is done in this mode. Okay. So, that it is much more protected mode. So, it is you cannot so in user mode you cannot access many of the system resources, but in kernel mode or system mode you can do that. So, that way there can be two different modes which are common in most of the systems. Okay. So, apart from that there are other modes as well, like we can have this user mode to run application code. So, this user mode is restricted in the sense that you cannot modify the CPSR register. Okay. So, that will be affected only by this arithmetic logic operations, but you cannot modify it by program instructions, and we can change the mode only via some exception generation. So, exception is like whenever you are asking for a device support, so that is an exception to the system. So, that is given as a system call to the operating system. So, that is an exception. So, that is so there can be different ways by which you can raise exceptions. So, you can change from user mode to other mode by raising exceptions. Another mode of operation is the fast interrupt processing mode or FIQ mode. So, this is one interrupt processing mode, but it is high speed interrupt, like whenever you are having say any embedded application, then all the activities are not equally important. Okay. So, all the events that are not equally important, like when we have got say a plant being controlled by say the ARM processor. Now, if they for the regular operation they have some priority, but if there is a smoke detector detects a fire situation or smoke is detected, so that is an emergency condition. So, the action has to take place immediately. So, that way, so that can be sent as a fast interrupt to the system, so that the response is much faster. So, generally a single critical interrupt source is connected to the FIQ pin. So, there is a dedicated FIQ pin in the processor and it is connected to that. So, this way we can have this maybe the power supply line is power failure is detected on the FIQ, connected to the FIQ. So, that if there is a power failure, the system will finish off the urgent works and then it will go to backup, then it will go to shutdown. So, and there is another interrupt processing mode which is known as IRQ mode, where the processing is, so it is other interrupts in the system. So, it is a ARM processor, it will have two categories of interrupt. One is first interrupt processing by FIQ and normal interrupt processing by IRQ. So, other modes of operation, like we have got supervisor mode. So, this is basically that system mode that I was talking about. So, this is entered when the processor encounters a software interrupt instruction. So, software interrupt instructions, so these are basically the feature that are used by that are provided by the system by the processor designers. So, these are interrupts, but these are some in a program you can put this type of instructions, like we can have the instructions like SWI, which is software interrupt, and a number n is given. So, what the system does is, depending upon the value of n, there is a pre-specified memory location where it will branch. Okay. So, this may be for SWI n equal to 10, maybe it will come here. Okay. Now, what the operating system does is that for different services like accessing printer, accessing display, accessing file, accessing keyboard, etc., it may define different services, and this corresponding service routines may be loaded in these regions. Fine. So, now in a program, suppose I need the printer service, and the printer service I know that the service number is 10. So, in my program I call this SWI 10. Okay. So, I will be accessing this routine which is the printer access. So, this is so this when this SWI instruction is executed by a program, so the system will go to the supervisor mode, and in the supervisor mode, so it will be doing this OS service. Okay. So, normally this is software interrupts are reserved for this OS services. On reset, ARM will enter into this supervisor mode, and then it will be going to user mode depending upon the operating system control. There is one undefined instruction mode. So, undefined instruction mode says that this fetched instruction is not an ARM instruction or a coprocessor instruction. So, it is the processor is continually getting instructions from memory. So, if the program that is loaded in the memory, it has got it is not loaded properly. Okay. Some of the instructions are wrong, okay, in the sense that they do not correspond to any of the valid opcodes. In that case, the instruction is an undefined instruction, and then the processor will go to this undefined instruction mode, and accordingly it will do some operation. Then there is an abort mode. So, this is if there is a memory fault. So, it has generated some address, the processor has generated some address, but that address is beyond the range of the memory chip that we have in the system. So, that is a memory fault. Okay. So, that way it will be going into the abort mode. So, all these modes are supported by the ARM processor. Now, in different modes, this ARM has got different sets of registers. So, this is the system and user mode, and they share these registers R0 through R15. So, these registers are marked for the user mode and system mode. So, these registers are common. Okay. Now, out of that I have already said that R15 is the PC, R14 is the link register, R13 stack pointer, generally like that we have said. Now, if you look into the FIQ mode, in FIQ mode you have got the registers R0 through R6. So, that is fine, but this R7 to R14, so these are new registers. Okay. So, this R0 to R6, so these are the same as your user mode registers R0 through R6, but these registers are new, they are not same as this R7 to R14, R14 that you have here, they are not same here, they are new registers. So, what is the advantage? So, it is similar to the bank switching of say 8051. So, whenever you are writing the interrupt service routine, so if you can restrict your interrupt service routine to use these registers only, okay, R7 FIQ to R14 FIQ, then you do not need to save any of the registers. So, in any interrupt service routine, when you are writing any interrupt service routine, so we know that if this is the body of the interrupt service routine, then before that, if this interrupt service routine say uses the registers say R1, R2 and R3, then before we start this interrupt service routine, we have to save these registers, save R1, R2, R3, and after this before returning, so we have to restore these registers. So, restore R1, R2, R3, and then only I can do return. Why? Because in the calling program this R1, R2, R3 might have been being used. So, in this interrupt service routine, before using those registers we should save them, and before returning we should restore them. Now, this is the overhead. You know that if for particularly for embedded application, if I am working in a real time environment and that interrupt has occurred, and now I have to save the registers before going into the actual operation. So, that way this is an overhead. So, if I use in the FIQ mode, we have got a separate set of registers R7 FIQ to R14 FIQ. So, if you use those registers only, then you know that they are different from whatever register the program the previous user program was utilizing. So, that way you can you need not do this saving part. So, you can forego this saving and restoring part. So, your ISR becomes much simpler. Okay. So, this can be done. Similarly, we have got this supervisor mode, where this only R13, R14 they are new registers. Then abort mode we have got R13, R14 as new registers. IRQ also has got R13, R14 as new register, same for undefined. Apart from that, so each of these CPSR registers, every mode has got the CPSR register, and there is a corresponding SPSR register which is saved program status register. So, whenever you come to a particular mode, so previous CPSR register is saved automatically into the corresponding SPSR register. So, that while you are going back, so you can copy this SPSR register onto the CPSR back and you can continue with that. So, that way we have got a large number of registers in this ARM processor that helps us to write programs using the register file, okay, that the programs will be faster. Then the CPSR register, so it has got the 4 important bits N, Z, C and V, which are negative, 0, carry and overflow. These are the most significant bits of this 32-bit register. There are some more interesting bits. Okay. So, these bit number 0 to 4, so they are reserved for the mode part. You have seen there are 6 modes, but this mode register has got 5 bits in it. So, you can, so that may be for future extension. Then there is a bit number 5 which stands for the T or the thumb instruction set. So, whenever this processor this ARM processor, it is using the thumb instruction set, then this T bit will be equal to 1, and when it is using the ARM instruction set, then this T bit equal to 0. So, there are some specific instructions by which you can switch over between the instruction sets, and by looking into this T bit you can understand whether it is using thumb instruction set or ARM instruction set. Then there is the bit number 6 is the F bit, which stands for that FRQ mode or FIQ mode. So, if the processor is currently in the fast interrupt processing mode, then this FIQ bit will be set to 1, and if it is in the normal interrupt processing mode, then this IRQ bit will be set to 1. So, this is the CPSR register structure. You see that this is much simplified compared to say other processors that we have seen so far. Next, we will look into the data types that are supported by this ARM processor. There are 6 different data types: 8-bit signed unsigned, 16-bit signed unsigned, 32-bit signed unsigned. So, we have got both signed and unsigned numbers. It can be 8-bit, 16-bit or 32-bit. Supports both little endian and big endian formats. So, in fact, there is a pin called big endian. So, if you this ARM processor has got a pin called big endian. So, if that is activated, so processor will take it as big endian format, otherwise it will take it as a little endian format. So, what is it like? So, it's nothing but a convention. Okay. So, if you have got say an instruction some data, say 16-bit data or 2-byte data, where the numbers is say 2434 hex. Now, if you are storing it at memory location 1000, okay, so one location, so if the memory is 8-bit, then one location is not sufficient for saving the number. So, you need to have it stored in 2 locations, 1000 and 1001. Now, in one convention, so we can put this 24 here and 34 here, and in another convention I can store 34 here and 24 here. So, in this case, in the second case, what has happened is that this lower order byte, it has been saved in the lower order memory location, and this higher order byte, it has been saved in the higher order memory location. Whereas, in the first case, this lower order byte has gone to higher order address, and the higher order byte has gone to the lower order address. But operation wise there is no difference, but these are the 2 formats that are followed. So, Intel follows this format, and if you look into the Motorola series of processors, so they will follow this processor. So, ARM has got both the facilities, both the little endian and big endian. So, this little endian means it ends with the little one. So, this is that so this is 34 will come to the lowest address, and that way. So, that way we will see some example later that will differentiate between this little endian and big endian formats. So, but ARM supports both, and most of the implementation they support only little endian, because supporting both is of no use. Okay. So, and as I said that this ARM gives licenses to the manufacturers. So, they will select one of these formats, and accordingly it will be the data path will be synthesized for that. Next, we look into the instruction sets. So, as I said that there are two different instruction sets in ARM. One is the ARM instruction set, which is standard 32-bit instructions, and we have got thumb instruction set, which is 16-bit compressed form of instruction. Now, these instructions can further be classified as data processing instruction, where it is doing the processing like say add, addition, subtraction, multiplication, etc. Then data transfer instruction, transfer between say the register pairs, register and memory, like that. Then block transfer, you can move a block of data from one portion of memory to another portion. You can do branching, okay. So, you can go from one location to another location, branch from there. Multiplication, then conditional execution and software interrupt. So, these are the various categories of ARM instructions that we have. Thumb instructions are more close to the standard microcontroller and microprocessor instructions that we are familiar with. So, it is a 16-bit compressed format. So, in 32-bit we have got two instructions. So, if you are accessing the instruction, so you will be getting two instructions at a time. So, that way the code density will be better, okay, and it is better than many of the CISC processors. So, that way it is a very nice thing that code density means per if I for a particular function. So, if I have to write say 100 lines of code in one processor and 50 lines of code in another processor, then the second processor has got a better code density than the first one. So, it is measured in terms of say memory bytes, how many bytes are needed for storing the program. Okay. So, that way the code density will be better, and there is a dynamic decompression in the in pipeline form. So, ARM thumb instructions are not executed directly. So, they are converted into ARM instruction and then executed. So, it is basically in the form of there is a decompression that takes place. So, that way thumb instructions are going to be slower than the ARM instructions.